In this video, I'm going to show you how to select procedures for calculating derivatives. We've got several rules at our disposal here: the product rule, the quotient rule, and the chain rule. And often when calculating derivatives, we have to choose between these rules or decide to use a combination of them. So in this lesson, we're going to practice figuring out how to differentiate an expression using some combination of these rules. Before we get started, let's just briefly review these rules. First of all, there's the product rule. Product rule just tells us how to take the derivative of a product. It says that the derivative is just the sum of two terms, and each term contains only one derivative. Now, the quotient rule for differentiating a fraction of the form u over v is similar in the numerator. We have two terms, each term contains a single derivative, but instead of the sum of products, as appears in the product rule, we have the difference of products. And remember, in this difference, order matters. It's always the numerator that is differentiated in the first term. So that's the hard part of the quotient rule. The denominator is easy. Denominator is just the square of the original denominator. And lastly, we've got the chain rule. And this chain rule is for differentiating a composition of functions. If we are applying some function f to another function g of x, then the derivative of all of this is just the derivative of f evaluated at g of x, and then whatever that expression is, you just multiply it by the derivative of g of x. So that's kind of intuitive because you're just differentiating each function, f or g, and then feeding in its original input, like g of x was the input to f, and x was the input to g. And then you're just multiplying all the results. So without further ado, let's dive into some problems. First of all, we're given that y equals x times natural log of x divided by sine of 2x, and we want to compute dy dx. So what kind of procedure should we use to compute this derivative? Well, the most obvious thing that jumps out to us is this is a fraction. There's a big old fraction bar in the middle there. And we know that for differentiating fractions, we use the quotient rule. So why don't we go ahead and start by using the quotient rule. And the quotient rule will tell us that dy dx, the result of that, is another fraction where the numerator consists of, first of all, the derivative of the original numerator, x times natural log of x, that times the denominator, sine of 2x, and then minus the original numerator, x times natural log of x, times the derivative, d over dx, of the original denominator, sine of 2x. And that's all over the denominator squared. So sine squared of 2x. Okay, so in here there are still two derivatives we need to compute. There's derivative of x natural log x, and there's derivative of sine of 2x. Why don't we go ahead and compute the derivative of x natural log x first? And this is a product of two terms. This is x times natural log of x. So, of course, we will use the product rule. And we'll just focus in on that single derivative there for now. Whatever we get as our result, we'll sub back into the whole fraction thing. But right now, we're zeroing in on this x natural log of x. All right, so according to the product rule, the derivative of that product is equal to the derivative of the first term, so d over dx of x, times the second term, natural log of x, and then plus the first term x times the derivative of the second term, natural log of x. So let's go ahead and compute that. Derivative of x is just 1, so 1 natural log of x, and then plus x times derivative of natural log. Derivative of natural log is just 1 over x. And let's simplify this a bit. So this becomes just 1 times natural log, which is just natural log, and then plus x times 1 over x. These cancel, and it just comes to 1. So that's what this derivative comes out to there. Natural log of x plus 1. Now we've still got another derivative of sine of 2x. And how do we compute that? Well, this is a composition of functions. One of the functions is 2x, and the other function is sine of that. So we'll go ahead and use the chain rule there. Chain rule tells us that the derivative of sine of 2x we can calculate by first just differentiating the sign part, forgetting about the 2x for now, just differentiate the sign and you get cosine, and then feed in that original input of 2x. But then you also have to multiply by the derivative of that original input, which was 2x. So this comes out to cosine of 2x times the derivative of 2x. Derivative of 2x is just 2, so this is really just 2 cosine 2x. Alright, so now we're going to go ahead and plug in these derivatives. We found that natural log of x plus 1 should go in for that derivative, and 2 cosine 2x should go in for this derivative. So plugging this in to dy dx, our big fraction there, we have that dy dx equals this big fraction. First of all, we've got our natural log of x plus 1, that times sine of 2x, and then minus x times natural log of x times derivative of sine of 2x, which we found was 2 cosine of 2x. And that's all over sine squared of 2x. So there we go. There is our derivative. That is dy dx. Next up, we're given that f of x equals e to the x squared power times tangent of 3x, and we want to compute f prime of x. Alright, so how do we take the derivative of this function? Well, there's a couple things that pop out to us. First of all, we see some compositions of functions. There's a function x squared here, which occurs as a power of e, and there's a function 3x here, which occurs as the argument to tangent. But even more important than that, right off the bat, is that we have two functions being multiplied together. There's this e to the x squared power times this tangent of 3x. And the product rule will allow us to split up this derivative into two simpler derivatives, derivatives of these two functions, e to the x squared and tangent of 3x, independently. So let's go ahead and apply the product rule here. Applying the product rule, we find that the derivative f prime of x is equal to the derivative of the first function in the product, derivative of e to the x squared, then times tangent of 3x, and then plus e to the x squared times the derivative of tangent of 3x. Alright, so now we have two simpler derivatives that we need to compute. There's that derivative of e to the x squared and the derivative of tangent 3x. Why don't we start off with the first derivative first, this derivative here. Since this is a composition of functions, it's x squared, that function, and then a function which is e raised to that power, we're going to use the chain rule. And the chain rule tells us that the derivative of that composition of functions is, first of all, just differentiate the exponential function, e to some power, and the exponential function, when differentiated with respect to its power, it doesn't change at all. So it stays as e to the x squared. But of course the power is actually a function of x, it's x squared, so we have to multiply by the derivative of that. So multiply by the derivative of x squared. And let's go ahead and simplify this. So this is e to the x squared, and then the derivative of x squared is just 2x. Using the power rule, just bring down the exponent and decrease it by 1. So just 2x, we can simplify that to just 2x e to the x squared. Alright, and then how about the other derivative over here? The derivative involving tangent. Well, that's again a separate function as the input. The input is 3x, that's its own kind of function that we're feeding into tangent. So again, we use the chain rule. So chain rule tells us that the derivative of tangent of 3x can be computed as follows. First, just imagine that we were differentiating tangent with respect to its input. The derivative of tangent is just secant squared, so we would have a secant squared, and then the input would stay the same as 3x. But then the chain rule tells us we have to multiply by the derivative of that input afterwards. So derivative of 3x. So let's go ahead and simplify this. This is secant squared of 3x times derivative of 3x, which is just 3. So this is really just 3 times secant squared of 3x. So we can go ahead and substitute these results back into the original expression. This goes in there, and this goes in there. And our result then is that f prime of x is equal to 2x e to the x squared times tangent of 3x, then plus e to the x squared times 3 secant squared of 3x. And why don't we go ahead and simplify this a little bit? So f prime of x, the thing you'll notice we can simplify here is we've got an e to the x squared in both of these terms. So why don't we go ahead and factor out that e to the x squared and then write what we have left over. Well, left over is our 2x tangent of 3x and then plus 3 secant squared 3x. So there we go. There is f prime of x, our derivative. So now we know how to select procedures for calculating derivatives. And in the future, we'll continue to learn how to differentiate even more complicated functions, including functions which are defined implicitly within an equation.